anemometer. We talked about, oh, remember this? We used a lot of these instruments. We're going to be using them again when we do that. We use the anemometers to measure the capture velocity. We talked about a bolometer. We didn't use it. That's more of a situation that we'll have with the HVAC systems. Now, how do we calculate what the hood needs in terms of static pressure to perform correctly? Well, we go to our tables. Some of these numbers come from the manufacturer of the hood or other sources that have actually tested the hood. Okay, some of these numbers come from calculations that are based on guesses or simulation of how we think air is behaving around the hood. In most of the calculations on chart 7, you'll see two formulas. You'll see a formula like this, and you'll see a second formula. They're all going to involve the quantity of air that's moving, the velocity. Which velocity is this? This V? Since we're dealing with a hood, there's a million velocities going on in a hood. So what's this velocity in particular? You guys remember? If you look at chart 11, they make it simple for you. They put a little c down on the bottom of it. That's the capture velocity, right? Because that's the only velocity you can work with, because you don't know what the velocity is here, velocity is here, velocity is here. It's all different in a hood. So in some cases, it's so turbulent in there. In some cases, you measure velocity, it's going the other way. Right? You have an eddy and it's turning the other direction, right? So there's a lot of nasty stuff going on in that hood. So the only practical velocity before you get 4 to 6 duct diameters up past this hood, the only practical place to really take readings is that capture velocity. And that's really what we're interested in. So the contaminant is going to be generated here at X. So you have X distance away from the face of the hood. What is that measured in what units? What do we always, in American units or our units, what do we always measure all of this stuff in, all of these things? V. V is going to be in feet, right? Feet, right, exactly. Feet, seconds, cubic feet, square feet, right? So X is, if I told you X was 12 inches, X in this formula is not 12 inches. X in this formula is 1 foot. Okay, V is feet per minute. Okay, so the capture velocity in feet per minute, say 100 feet per minute, 200 feet per minute, really nasty contaminant, maybe 250 or 300 feet per minute. We want to capture that at that distance away. Why that distance? Because that's where it's being generated. Okay, not necessarily closer, not necessarily further away, but at that distance where it's actually being generated. Okay, so we're going to calculate from that. The A is the cross-sectional area of the face of the hood. Right? Whatever that happens to be. This flanged hood, you're talking about the inside area here, right? The actual hood itself, whether flanged or not flanged. The flange is made up for by this formula being a slightly different form, 0.3 of the volume that you need. In other words, to get the same capture velocity, you need 3/4 of the volume that you would need for a unflanged hood of the same size, right? You need less air movement for this one than for this one. Why is that? Because this one wastes air. It wastes air because it pulls air around from the sides in addition from the direction you want it. This one doesn't do that, right? So you need less air movement in here. These formulas happen to be based on imagining a bubble around this thing and X distance from all directions, the air moving from X distance into this hood. Now, some of these formulas, the second set of formulas, might be provided by the manufacturer or they might be provided experimentally, and they might actually, since they're actual measurements of the performance of the hood, they might actually be a bit more reliable than the theoretical numbers that we might have here. Okay, now an important aspect of this, the ratio, the aspect ratio, it's the ratio of the width to the height. In other words, it has to be 0.2 or greater or round the opening of this thing, right? 0.2 or greater, what does that mean? That means that it's got to be the width, the height has to be at least 20% as big as the width, right? So if I have one that's 0.1, the aspect ratio, what does that look like? That looks like a slot, right? we use a different formula for slot hoods. Right? So it's not that that's such a horrible formula to use, but that there's a better formula for that. So this is for situations where the ratio between the width and the length is at least 0.2. Okay, in other words, not more than 5. The length is not more than 5 times the width. Okay, and in which case it would appear more like a slot than it would like a rectangular hood like this. Okay, let's see. Okay, I wouldn't worry about this too much. We go through this. These are some calculations, typical calculations. I'll post. This is posted on Blackboard. Coefficient of entry for hood. That's the actual volume of air that you need to achieve the velocity that you want, divided by the ideal volume of air. Hoods are not perfect, right? So a hood, because a hood is always going to pull air from spots you don't need to pull air from, right? Then what happens is Q actual is a bigger number than Q ideal, right? So the coefficient of entry is going to be this fraction, the level of actual, it's a measure of efficiency. In other words, if you need twice as much air as the ideal situation to get the static pressure that you need to get the hood to work properly, well then the coefficient of entry it reflects a bigger number and represents a higher level of loss or less efficiency. Another measure of efficiency is actually they show it inverted. Okay. Another measure of efficiency. Remember what the other measure of efficiency? We're going to come across it in a little while, right? HE, hood entry loss, is another measure of efficiency. Design. We have various designs, slot hoods. What happened? What they do here? This is a slot hood, but they added something to make it more efficient. What did they add? The side panels, right? How do the side panels help? They restrict the air being pulled in from the side where it's not doing anything effective for you, being pulled in from behind or from the side, and so on and so forth. It also restricts the airflow. Now, what else is going on here that's helping out? You got air moving here. What else might be happening here? Well, look at this air supply. At the same time that it's sucking air away from pulling the contaminant away by sucking air away, it's also blowing air in the direction of the hood. So it's encouraging it to form a curtain there. We always need this particular situation is kind of a pull-push situation. It's pushing the contaminant as well as pulling it at the same time. Does that mean we don't need? Does that mean that most hoods are not going to need an air supply? Right. We forgot one. Remember we talked about the components of an effective exhaust system: the hood, the ductwork, the cleaner, the exhaust duct, so on and so forth. We left something out there, didn't we? What else do you need to make it work effectively? You need makeup air, right? If I have this room and I have a big exhaust, if I have a hood in the corner of this exhaust fan, a corner of this room, and I have all the windows closed, the door closed, and so on and so forth, you're not going to be able to suck air out of this room. The hood's not going to work, right? You need to be able to pull air out of the room effectively in order for it to work. Right? If you have a boiler at home, if you have like a private home and you have like a small boiler in your home, you'll notice that somewhere the guy that installed the boiler probably put a little louver on a little window or through the wall of the basement or something like that so that air can come into the basement, because it won't exhaust properly unless it has makeup air. So almost any time you see a device like a hood, a smokestack, anything like that, that has to exhaust hood from a location, you're also going to see some mechanism for makeup air. Okay, here's the system. Vena contractor, remember that? That area is right at the face of the hood. Extreme turbulence. Okay, static pressure. Static pressure at the hood is equal to the velocity. Remember we talked about the velocity pressure the static pressure and the velocity pressure related. One's potential energy is a kinetic energy. In a perfect situation, perfect hood with no losses and so on and so forth, the static pressure is going to be the same thing as the positive value of the velocity pressure. The only difference here is going to be that the velocity pressure you're also going to lose some of the velocity pressure to losses. You're not going to convert all of that static pressure energy, that kinetic energy, to that potential energy to kinetic energy. And that's where the quantity of pressure that you lose to the hood is called the hood entry losses. Okay, so you might come across this formula. It's shown as a positive value so you can see that relationship between the static pressure and the velocity pressure. Most of the time, we're going to see it more frequently in terms of static pressure losses equal to some factor times the speed that the air is moving. In other words, the velocity pressure times the density correction factor. Again, most of the time we're not using it for the moment, but it'll come up later on. Okay, and you can use these formulas in various formats. We saw that for all these different devices, we frequently have a K value for the elbows, for the ductwork, for the transitions. We have a value K, which represents the amount of loss that we can expect, and it's related to how fast the air is moving. The faster the air moves, the greater is the frictional loss, right? And in each one of these transitions, when we calculate it, we're just taking that K value for that particular device and multiplying it by the velocity of pressure to figure out how much static pressure we have to make up for because of that loss. Okay, here's some additional hoods and additional formulas. Here's one with two formulas. One formula based on the idea of that imaginary circle, and the other formula based on the actual manufacturer's recommendations. Okay. Okay. We have a few tables that for different kinds of particles or contaminants recommends transport velocities, capture velocities, and transport velocities. Okay, so you might want to consider that. You have in your references, you have the correction factor for different kinds of ductwork based on how smooth or how rough the material is. Corrugated flex duct, correction factor is 2.6. ABS plastic, it's 0.9. The reason this correction factor is based on galvanized iron because most ductwork is galvanized iron. So this is a correction to your K factor. If you're using standard galvanized iron ductwork, then that K factor that gives you that, helps you calculate that loss, is multiplied by R of 1.0. In other words, you can forget about the R. If you're using very smooth fiberglass or PVC pipe, then you can reduce that K value a little bit by multiplying it by 0.9. If you're using flex duct, that's much more turbulent, loses a lot more energy, so you have to multiply that K value by 2.6. You don't really see it that way in the formula. You see it as K times R times the density times so on and so forth, times the velocity pressure. There you go. K times the velocity pressure times the length of the ductwork times R times D. For galvanized iron, the R is 1. For standard temperature and pressure, the D is 1. So the only thing you're worried about is the length of ductwork, the loss that's introduced by that ductwork, K, and the velocity pressure, which you can figure out from the velocity. Okay, elbows. Elbows, in order to find that K value, you have to know how smooth the transition is. Okay, and so for a 90-degree turn, okay, that's related to the number of sections that you have. The more sections you have, the closer it is to a perfect curve, the less transitional friction that you have. So first thing we have is a number of sections. So you have a smooth surface like PVC or something like that, and that's this first row. And then it gets progressively greater losses based on 5-section, 4-section, 3-section, because there are more abrupt turns. And the ratio of the radius to the diameter of the ductwork in feet again also impacts the rate of flow. So you just combine these two. So if the radius of the turn is twice the diameter of the ductwork, we use this column here. And if we're using a 4-piece elbow, then our K value is going to be 0.24. 4-piece and radius to diameter ratio of 2. It's 0.24. That's how we would calculate K. Then we use 0.24 times the velocity pressure, gives us the amount of loss that we expect through here in static pressure. So now, the other thing that's interesting about this is that not all turns are 90-degree turns. So what if we're only making a 45-degree turn? What do we do there? Half it, right. What if we're making a 30-degree turn? It's 1/3 of the 90-degree turn. We just assume that for good enough for our measurements that that's the way we're going to estimate the. Yeah.
How do you get that? How do you determine the R/D again?
I'm sorry, the R.
The R/D. How do you determine that?
Well, for instance, let's say that this ductwork. Whoops. Let's say that this ductwork is 12 inches in diameter, right? If you look, the radius of the turn, if I put my little pinpoint here, like as if it's a compass, this radius from here to there, right? The radius of the actual turn is, let's say, to me, it looks like it's roughly 2. This distance looks roughly 2 times this distance, right? Well, actually, it looks more like 4 times it, doesn't it? Because it would be the radius here, right? So this radius, this distance here is the radius of the turn. This is the diameter. Actually, it looks like 2. This is the diameter of the ductwork, right? Diameter of the ductwork, radius of the turn from here to here. So now, if this ductwork were made a sharper turn, right? Let me draw it.
This is all going to be provided in the problem, right?
I would think so. Yeah. Yeah. They'd have to tell you that, right? They might give you the radius of the turn and the size of the ductwork, so you have to figure out what R over D is, right? Right, but I mean, yeah. For instance, let's say we have ductwork that's 12 inches in diameter. Remember, one's radius and one's diameter, 12-inch diameter. Okay. So now, this ductwork, if it turns like this, right? This is 12 inches, right? Now, if you look at this radius, I turn this into a whole circle, the radius, the center of the circle is here. So the radius here might be 24 inches, right? So that's the radius. This is diameter of the ductwork. This is the radius of the turn. So that's 2 feet, right? This is 2 feet over 1 foot, and the R over D is equal to 2, right? On the other hand, you could have a much sharper turn. Here's the same oops. Let me do this a little bit better here. Here's the same 12-inch ductwork, right? But the radius of the turn is much sharper, right? So this could be 12-inch radius here, 12-inch diameter ductwork. So the radius over the diameter is going to be 1 foot over 1 foot. So they're both 12 inches. So it's a sharper turn, right? Where you could have like a really slow turn, right? If this is 12 inches, it makes a 90-degree turn, but the radius is very large. Okay? It's like going around a much larger curve. Go around a tight curve, you feel the G-forces a lot more. Same thing with the air. That's basically what's happening with the air. How am I doing on time? Oh, geez. My goodness, there's so much stuff we covered. Isn't there? Jeez. Let me see if I got any comments here. Uh-oh. My goodness. Okay, let's see. Did I have any questions there? Okay, I see you guys there. Okay, I'll try and check in. I didn't realize anybody was there but Grace, so I'll try and check in a little bit more online. Okay. Not that I wanted to, belittle Grace being there, but I meant students. Okay, so this is the deal. Here's transitions. We got the same deal. Through each one of these transitions, we're going to lose some energy as well. So the velocity is going to change through each one of the transitions, and the K value that we calculate through here, it actually uses the angle of the transition, the taper angle of the transition, and the velocity change. That's K times the change in velocity is how you calculate that loss. So that's a little bit different. See, static pressure 2 is equal to static pressure 1 minus the change in velocity times that K value. Okay, so that's a little bit different. There's the tapered, the K values for the different tapered transitions. Okay, and then you get complex kinds of transitions. A lot of times these are transitioning from round duct to rectangular duct. There's a blast gate. There's a system design balancing we talked about before. I'm gonna go. Oops, I guess was that it? Guess I was further along than I thought we were. Yeah. Okay. All right. So what I want to do next is I just want to go over what we were talking about last week, and I'm going to hand out the sheets that we were using last week, if I have them. I know I'm killing you by hitting so much of this. Can't be too pleasant running through this stuff so fast. Okay, here, pass those around. Okay, 2 pages. Page 1 and page 2 for each of you. Okay, for you guys online, what we're looking at now is we're looking at part of that, the class exercise that we did last week. That involved the tracking of an exhaust system. Okay, in this first one, okay, you're going to need 2 pages there. This is the first of the 2 pages. This is the second of the 2 pages. Okay, in the first of the 2 pages, the effect of all the transitions is already calculated for you, is already laid out for you. Let's take a look at them. Okay, so at the hood, outside of the hood, the static pressure is 0. Just static pressure is 0 gauge, right? With hoods, Can you see that there? No, you can't. I just lost connection. Okay, let me give this a second. See if I get these guys back. I lost them momentarily. Hope they come back. I'm going to have to move forward. Okay, I don't want to kill too much time. Can you see me moving anything back there? Is it standing still? No, yeah, they're stuck right there. Okay. So I lost the connection there. That's why that stopped there as well. Oh, it's a Wi-Fi problem. I'll give it another second. Okay. Hopefully the recording will still work because that's, I think, working on my computer. Okay, so let's take a look at this. Here's our duct system right here. Here's our hood. Outside the hood, static pressure is 0. At the hood, we have a complex situation. They show it as static pressure negative 0.02 or something like that at some point in the hood, right? But really, the place where we're measuring the performance of this hood is right here. The static pressure for the hood is negative 1.2 inches. We're measuring it right there, a few duct diameters up from the hood. How do we know what that has to be? How do we know what that static pressure has to be at that point in order to get the capture velocity we want? In order to get the capture velocity that we want at this point, right here, right? That's right at that point over there, which is some distance in front of the hood. We want a certain capture velocity. How do we know what the static pressure has to be? We look at that formula. What does that formula ask you for? The capture velocity, the distance from the hood, the area of the face of the duct, and what does it wind up giving you? It gives you the quantity of air, Q. Remember, Q is equal to all these things. Gives you the quantity of air that you need to get sucked into this hood, cubic feet per minute, in order to give you that capture velocity you need. If you know the quantity of air, what do you know about the air moving through this duct? You know its velocity, right? So if you know its velocity, right, what can you calculate for that? You can calculate the velocity pressure. You can also measure the total pressure and the suction pressure. You can measure the suction pressure at that point. In fact, if you know this hood well, if you know the formulas for the hood, you can calculate what the static pressure has to be at that point for this hood to work properly. So we know this static pressure at this has to be negative 1.2 inches. So now we have a run of ductwork, an elbow, and some other losses. So we know the static pressure here has to be negative 1.6. Static pressure before the filter, in order for us to have a static pressure after the filter of negative 1.6, it has to be negative 2.6, so on and so forth to negative 3.0. We're going to plot all of these here. Okay, so if I go down here, I'm frozen on that screen. So if you look at the first, if you look at your second page, okay, what you see on your second page is you see a simplified version of this ductwork. Yeah, I'm just not getting it back. Yeah, Wi-Fi for some reason has disappeared, has abandoned us. I'm sorry I didn't plug in. Looking for networks, yeah, just the Wi-Fi went down. Oh, that's unfortunate. Okay, so at any rate, if you look at that, oh, connection restored. What do you know? Oh, I guess I am muted. Okay. Okay, you should be able to hear me now. Again, you guys, most of this should have recorded, so you'll be able to see it later on if you've missed portions of it. Okay, actually, there's no way to mute me in this room, so the people that are here actually can hear me, believe it or not. That works. Okay, so at any rate, I'm going to move this over. Okay, so boy, Wi-Fi has really gotten undependable in this place. Okay, so let's look at this point just after the hood. Okay, diameter of the ductwork is 16 inches. The velocity is 3,580 feet per minute. The total pressure is -1 inch of water, right? Static pressure. Let's fill in the rest of this. Anybody got any ideas? How am I going to calculate the area? Right? So, all right, yeah, okay, pi r squared is equal to 3.14 times the radius squared. What's the radius? Radius is, what's the radius of the ductwork? What's the diameter of the ductwork? 16 inches. Radius is 8 inches. What units do we need?
0.6.
Yeah, 0.67. I'm going to write by 0.67 times 0.67, radius squared. Right? Because it's got to be in feet. Right? So it's 1.4 square feet. Okay, so now that we know that's the area and this is the velocity, what else do we know about this system? Well, we know the quantity of air that's moving through this system, right? Okay, we also should be able to pick out, well, what's the velocity pressure going to be equal to? It's 4,000, what is it again? It's going to be, what was the formula that we used before? We have to, okay, it's going to be the square root of, what is it, the velocity divided by 4,005. Am I right there, or did I reverse the formula? Oh, I have to square, wait a second, I got to square it. Hang on a second, I got this wrong. Hang on a second, let me do it this way. I'm sorry, say again? Okay, I'm going to do it out here. Equals 3,580 divided by 4,005. Okay, and then I'm going to square that in here. Equals this times this. So the velocity pressure is 0.8, basically 0.8 inches. So if the total pressure is -1 inch and the velocity pressure is 0.8 inches, what is the static pressure going to be equal to? It's going to be equal to the velocity, it's going to be equal to total pressure minus the velocity pressure. Okay, -0.2. Okay, whoops. Okay, hopefully that'll work. Okay, so now in the next segment, in order to achieve that, we're going to have a larger negative pressure here. In fact, it's negative. How did we get this? Oh, okay, we got that. Yeah, notice the velocity pressure we just calculated was what, 0.8? Notice what at 0.3 what the velocity pressure is. It's the same. Makes sense, right? We expect the velocity throughout to be the same unless the duct diameter changes. So our calculation here is right. In fact, we didn't even really need to make this calculation, did we? We could have just looked there and realized it had to be the same. Okay, so now what's our velocity here? What's the velocity going to be equal to if the velocity pressure is equal to 0.8? It's 4,000, what is it?
4,005 times the square root of that.
Okay, 4,005 times the square root, oops, of the velocity pressure, which is 0.8. Okay, so again, the velocity is the same as it was before. Again, we didn't really have to even do that calculation, right? There's a rounding error there. You get why these numbers are the same? Right? And in fact, you want to know something, unless there's a change in the size of the ductwork, which is about to happen now, there's no reason for that to change. Okay, so what's the cross-sectional area here? It's also going to be 1.4. Okay, and let's see what we have now. So now the ductwork is now going to change size. The cross-sectional area now is going to be 1.67, right? So what is the velocity going to be instead? Well, Q has got to be the same as it was before, right? So what was Q before? Right? So let's say Q is equal to the velocity times the cross-sectional area. Okay, is 5,000. So now I want to find out what the velocity is here. I know the diameter of the cross-sectional area of the ductwork, and I know Q, right? So I know Q and A. So I want to find out what V is. So V is going to be equal to Q over A. So it's going to be equal to Q. The volume's got to be the same, divided by the cross-sectional area of the ductwork, which is 1.767. So the velocity now is 2558. Okay, why is the velocity lower? Because the cross-sectional area is larger. Okay, so now what's the velocity pressure equal to? Got to do the same deal, don't we? Now, before I actually do the calculation, do you see something that'll tip me off to what the velocity pressure is before I even calculate it? Is there any change in diameter here versus the diameter here? No, there isn't, right? So the velocity pressure must be the same because the velocity is going to be the same unless the duct diameter changes. So this is 0.5 also. Okay, so that's what the velocity pressure is. Okay, so now what about the, let's see, what else are we missing here? Now, what was the transition there? 4 is, where was 4? 4 was, now we're on this positive side of the ductwork. 25, Q equals 5,000. I don't know where it got Q equals 5,000 from based on these areas. Let's see. 3580. Oh, I did get 5,000 for Q. Okay, yeah, Q is the cross-section of velocity times the cross-sectional area.
So that's 35.
From here. Any one of these, the Q is going to be the same. Velocity and cross-sectional area on any one, it's all going to come out to be 5,000 because the amount of air that's moving through there. Okay, so we got the velocity pressure. So now the static pressure, let's see, 15. So let's see if we can't figure out what these pressures have to be. So this is 1.767. The quantity of air that's moving through here is the same. The velocity is the same, 2855. Right? And now we're left with what's the total pressure here? Total pressure here is going to be equal to the velocity pressure plus the static pressure. So we have those all worked out. So now, what is the total pressure and the static pressure here? Well, that gets a little bit more complicated now, right? So how are we going to figure out the total pressure and the static pressure here? Well, the static pressure here is 1 inch. The static pressure here is going to be higher than 1 inch or lower than 1 inch. Static pressure here is going to be higher, right? Because the velocity pressure is going to stay the same. Static pressure here is higher because we're going to lose static pressure as we move through this ductwork on the discharge side. So it's going to be higher. How much higher is it going to be? Well, in order to figure that out, we have to figure out what the loss is of static pressure in this length of ductwork. And in order to know that, we have to know the length of this ductwork. Okay, so down here, they gave us the frictional loss in, I can't read that, can you? 0.55 inches per 100 feet. Is that what they have there? Right? They didn't give us K factor, they gave us per inches. Did they give us a length? They should have given us a length. Oh, here it is, length's right here. The length from there to there is 50 feet. So the length is 50 feet, so how much static pressure are we going to lose between here and there? We're going to lose half of that 0.55, right? Which is roughly 0.27, let's say. Am I right? Yeah, 0.27. So roughly 0.27 inches is going to be a loss in our static pressure. So this is going to be equal to 1 minus 0.27. A little convoluted, and what's our total pressure? Is going to be equal to this plus this. Okay, so it's a little convoluted. Oh, I'm sorry, this is higher. This is plus 0.27. Right, that makes sense now. We lose some static pressure on the discharge side because we're going through that 50 feet of ductwork. So what have we accomplished here? We found all of the velocities and pressure through this run of ductwork. So now that we've done that, we can actually sit here and plot them on the graph paper that you have there. So let's just look at the static pressure. What are the static pressures going to be doing here? It's going to start out at 0 at the hood face, and it's going to go quickly down to negative 0.2. So I'm going to go up here and get a,
Tony,
that's a PDF file. I'm going to go up here and get a
Tony.
line. Okay, and it's going to go from basically 0 to negative 0.2, like so. And then from there, from 0.2 to 3, it's going to go to 2 to 3.
Yes.
It's going to go to is it that low? Which
We
side
are
of the
on
fan
mute,
is that?
so he can't hear us in the room.
I lost which side of the fan I was on.
But
Two
yeah, and I
to
typed, if you can
three.
see, I typed several
Yeah, static
messages
pressure drops
to
quite a
try
bit.
to
There must be an air filter in there
freeze.
for the static pressure to drop that much.
So
It's gonna
he
go
checked
from
in a
there
couple of
to-
times, but I don't think everyone was online.
So remember that
But
we didn't actually calculate that. They
I was
gave us that
responding to your
value.
Questions that
Let's get another line. It's going to go from there
yes,
to
and
negative
so if you stay
2.3.
on it, because he keeps checking, but sometimes nobody responds. So I think you had
Across
stepped
the
away.
fan, it's going to go to a positive
It's all
number of static
recorded.
pressure.
If you look
It's
at
going to go up
the,
to 1.27.
go ahead and follow what he's doing now. But if you look at the equation,
Oops.
you'll see why he had the 50.
1.27 is going to be roughly up there. And from there,
Okay,
it's
just
going
come
to
back
go,
in a few
we're going
minutes.
to lose a
I'm not
little
a
bit of
50
static
follow
pressure
him.
because
I
it's
have
going
the
to
50
lose some
feet. I
energy
got
on the
that.
way out. It's
The
going to go
half,
to 1.0, I guess,
after the 50 feet,
when
what
it
did you
comes
get
to
the
the
rest?
exhaust stack. Okay, so there's our plot of static pressures. Now we can do the same thing
Oops, I
for our
muted. Okay,
velocity
come back to that.
pressures
But
and for
follow
our
what he's
total
doing now
pressures
and then just loop
using these
back
various
to
numbers.
that once he's finished. He's
Okay,
going to
makes
check
sense?
in again.
Okay,
So, quick question.
Yes.
The 1.27,
thank you.
the 0.27, right? How did you get that again? You did 0.55 times 50?
Well, what did they give us again? Now normally when we design the ductwork, right, we would estimate how much the loss is using K for that ductwork, right? Whatever K is. So if it's galvanized iron ductwork of a certain diameter, we would use K is equal to 0.013, let's say, and we multiply it by the number of feet of ductwork. In this case, they gave us a summary factor. They told us that for 18-inch duct, the loss of pressure, the loss of static pressure is equal to 0.55 inches per 100 feet, it looks like. I hope I'm reading that correctly, right? Yeah, let me see if I can't blow that up. View, zoom in. Per 100 feet. Can you see it there?
Yeah.
Right, so they gave us the loss per 100 feet. Normally we would have K. What is K? K is the loss per foot, right? So the equivalent K would be 0.055, right? 0.0055 inches loss per foot. So we would be multiplying the velocity, actually we multiply the velocity pressure times K. In this case, they're just telling us what the static pressure loss is in inches per 100 feet of ductwork. Right? Normally we would have a K factor that we would multiply the velocity pressure by to get the amount of loss that we have, times the length of the ductwork. But in this case, they just gave us a factor. They didn't give us the one for 16 because they actually gave us the pressures that we needed. We didn't need to figure that out. In fact, we could figure out if we wanted to what the frictional losses per 100 feet is for 16-inch pipe based on the numbers that we got in our spreadsheet. Okay, makes sense? Okay, it's a little convoluted, a little bit different than the design would be, but I think that if you're a little bit patient with it, if something similar shows up on the test, I think you'll be able to work through it. If you just are calm and just make reasonable, work through the various things that you know. Like for instance, if we have the velocity pressure is 0.8 inches in the 16-inch ductwork on the suction side of the fan, well, at 0.2, it's got to be 0.8 inches also because the velocity, since the duct diameter didn't change, the velocity didn't change, right? If the velocity is 3580 in this portion, then it's got to be 3580 here. On the 18-inch side, if you know what the cross-sectional area is here, you know that the quantity of air moving through this ductwork can't change. So you know the velocity and you know the cross-sectional area on this side of the ductwork, so you can figure out what Q is. And once you know what Q is the same throughout each one of these points. So you could divide by the area and get the velocity, which gives you the velocity pressure, and so on and so forth. So it's kind of one step building on another. You ever do a crossword puzzle and you don't know the answer going down? You work on a cross and then you kind of fill in. If you do that with this kind of table, with these kind of calculations, then by filling in other portions of it, you'll realize that you know more about what's going on than you thought you did when you started the table, especially with all these blanks here. Okay, guys, good night. And hopefully you guys online, I'm sorry that you had an interruption or two. Okay. Okay, now Fanta, let me give you a few moments here. Tell me about what problems that you were having there, and hopefully when I post this, the recording, that you'll catch up with the portions of this that you might have missed while we broke away. Yes. Oh yeah. Hang on a sec. Hang on a second. Let's make sure. Yeah, straight. Okay, there you go. All right, let me know if you have any issues with it. Let me know if it works and stuff like that.
Okay,
If there's any individual
Professor
files or
DeVito?
anything you have a problem with, just give me a buzz. Hey, good night, guys. Sorry this was a little dry, but it was kind of hard to go through all this material without just kind of rushing through things.
Yeah.
Okay, and
well, I think when you post that Google Doc thing, that'll be really helpful.
Yeah.
As we're going through the thing, we can ask like certain topics.
Excellent.
To clarify.
Okay. All right. Hey, good night, guys. Okay, Fanta, hang on a second. The 1.6, remember that these values, Fanta, are the ones that are we were given. This raw data here is the ones that we were given. That 1.767, that's the cross-sectional area of 18-inch ductwork. Okay. In fact, we could have figured that out just by taking 18-inch ductwork. The diameter is 1.5 feet. The radius is 3/4 of a foot. We want to work in feet, not inches. 3/4 of a feet. So cross-sectional area of a circle is pi times the radius squared, or in other words, 3.14 times 3/4 times 3/4, and that comes out to 1.767. On this side, the radius was 8 inches, which was 2/3 of a foot. So the area we would put in here is 3.14 times 0.67, 2/3, times 0.67 again, and that would give us a cross-sectional area here. In fact, I closed that file, but it wound up being a bit smaller, and it was about 1.5 feet or something like that, 1.5 square feet. Hey, good night. Okay, and the velocity pressure, we use that formula. The velocity is equal to 4,005 times square root of the velocity pressure in order to figure out these numbers here, except we use it in two forms, one solving for the velocity pressure, the other solving for the velocity. And the static pressure, we figured out by subtracting the velocity pressure from the total pressure. We had a formula that says total pressure is equal to velocity pressure plus static pressure. If we know two of them, we can solve for the third. So if we know the velocity pressure, which we figured out based on the velocity, and we want to calculate the static pressure, well, then we know 2 out of the 3 unknowns in that equation. Total pressure was velocity pressure plus static pressure. So we solve for the static pressure, and I think it came up to be a pretty small number, like -0.2 or something like that. Okay, these were given to us, and then as we continue along, the velocity pressure, since we know the quantity of air that's moving through here is, they gave us 5,000 feet, in fact, cubic feet per minute. We know that Q is 5,000 cubic feet per minute. So the velocity, Q is equal to V times the cross-sectional area of the ductwork. So Q is equal to 1.7, Q is 5,000. So 5,000 is equal to the velocity times 1.767. Okay, unfortunately, I really can't make you look over my shoulder on this as much as I would. So since you know Q and you know A, cross-sectional area, you can solve for V. Okay, so that would give us the velocity. Velocity is the velocity pressure, and so on and so forth. And the same thing here. We know the cross-sectional area, the ductwork hasn't changed, so it's the same number here. Cross-sectional area didn't change, so the velocities, two velocities stay the same. So we filled in everything except these last two boxes. These last two boxes get a little bit more complicated because we know the velocity pressure, and which we just calculated from the velocity. And now we're going to calculate the, it's actually going to be the same as 0.5 because the velocity is the same at these 2 points. So now we need to calculate the static pressure. This formula here tells us for every 100 feet of ductwork, we lose ½ an inch of static pressure. So this static pressure has to be a ½ an inch different from this static pressure. Okay, so hopefully if you're still there and you can still hear me, it'll help you out with this. Now, as you're working on the exam, email me. Okay, I'm going to send out that Google Groups thing so that you can post questions and comments or requests for clarification and stuff like that, so that when I answer your questions or if I answer somebody else's questions, everybody else that subscribes to that group is going to be able to see those answers. We can do it on Blackboard also, but I think Google Groups actually works better.